Hi guys, Mr. Kane here.
Morning, Mrs. G.
Good to see you guys. Alright, this is one of those things we do every once in a while, isn't it?
Well, oh God. Yes, periodic trends.
Every once in a while we do these periodic trends.
Am I to assume then from the term periodic that we are going to use the periodic table to determine trends?
Yeah, I think so.
I can't imagine what else it would be.
Well, do you have your periodic table?
I do.
Alright,
I always have a periodic table handy.
Here's mine right here.
Oh God, you would have one of those.
Alright, so periodic trends are properties that are predictable based on their position on
Periodic table.
the periodic table.
Makes sense.
So they're properties that are predictable based on the element's position on the periodic table.
All right.
Alright. They're affected by a few things. One, they're affected by the number of energy levels that an atom has.
Yeah, because the energy levels go 1 through 7.
Right, so basically you're thinking about how many clouds are around it.
Or orbitals.
Alright.
Nuclear charge, so the number of protons in each element.
Alright.
Electron shielding.
Which is the amount of electrons in between the nucleus and the outermost electrons.
The valence electrons, so the
Right.
core electrons.
Right, the core electrons, yeah.
Okay.
Electron shielding are the core electrons, the electrons inside. Alright. And also electron to electron repulsion.
Yeah, because they're equally charged, or not equally, they're the same charge, so they would repel each other.
And electrons are repelled by each other, they're repulsive.
Yep.
So the very first trend we are going to talk about is a trend called ionization energy. What do you think that is, Mrs. G?
Well, I'm pretty sure I know what it is, but I'll tell you one thing, I don't write that all out. I write IE for short, and ionization energy is the amount of energy it takes to remove an electron from a gaseous atom.
Ooh.
So the trend is that ionization energy increases from left to right.
Yeah, so it gets tougher to take away an electron as you go from the left side of the periodic table
Takes
to the
more
right.
energy. Okay.
So if I'm in the second group, lithium's easier to take an electron away from than beryllium.
Takes more energy to get beryllium's valence electron away from it than it does to take lithium's valence electron away from it, correct?
And the hardest one in that period would be neon. You would have the hardest time taking neon's electrons away?
That's a noble gas. Noble gases are relatively inert. They don't like to gain or lose. But if you got enough energy, I suppose you could do it.
All right, so from left to right, that seems to make sense. The fewer electrons, the easier they give them up. And that makes sense because that's something that we've talked about before. Decreases from top to bottom. So if I'm talking about group 1 there, between lithium and francium, it decreases as I go down. So it's easier to take an electron away from francium.
Correct. Don't forget they both have the same number of valence electrons.
1.
But francium has 86 core electrons hiding that one, or shielding that one valence electron.
Okay, so those electrons in the core are actually shielding the outside electron in francium.
Yep.
Whereas lithium has two core
Two
electrons.
core electrons. Yeah, that's not a lot of shielding.
All right. Ooh, here is a graph of it. So we could write in here that this element would be hydrogen and helium here.
Yep.
We got lithium and beryllium.
Beryllium. Boron is a little anomaly. Boron's a little exception to the rule because it goes down a bit. Carbon, nitrogen, oxygen, and that's an exception to the rule, goes down. Fluorine, and neon.
Well, the whole point, this isn't perfect. This is a trend, right, Mrs. G?
Yeah, it's a trend, and that boron oxygen, you know what that's got to do with? It's got to do with partnering up for the first time electrons. There are anomalies all over the place, so.
But the trend is it goes up. If I just look at this graph, the trend is the graph is and then here's the group. It starts with sodium and it ends with argon. So the trend here is that we're just going up.
Yep, and if you notice, the anomalies or the strange oddities are in the exact same place as they are in the first boron oxygen.
Now with successive ionization energies,
we're talking about the same atom, right?
Right, same atom, just before we were talking about the first electron. Now we're talking about taking away the second or the third electron from it. After the first electron is removed, the nucleus grips the remaining electrons stronger.
Okay.
It doesn't have as many to pull in, so it can actually pull them in even tighter.
Yep.
Therefore, it gets harder to remove each one because they're closer.
So each successive ionization energy will be a larger number.
Correct. Yeah. And here's an example for magnesium. The first ionization energy for the first electron is 736 kilojoules. It turns out that the second ionization energy is 1,445.
So it increased, and magnesium has 2 valence electrons.
Right, and it's reasonably easy to take away the first 2 if you look. But
Yeah.
the third one, that's a core electron.
That's almost an increase of 7-fold. That's
Yeah,
huge.
That's a huge increase.
Oh, so the minute you start digging into the core,
They start getting really difficult
it's a
to
big
do.
jump. So you could actually determine the atom, or at least the family of the atom, based on ionization energies.
Mm-hmm.
Whichever one gives you the greatest leap, that's the last valence electron, and the very first core electron.
Right.
Ah.
Okay, atomic radius. So the atomic radius is very similar to the radius of a circle, right? Because atoms are kind of like circles.
Yeah, but it's measured differently because we give them a defined edge. There's really no defined edge on an atom.
Yeah, that we can't really measure. Yeah, we can't
Right,
define that edge,
there's no
so it's
defined
difficult.
edge.
So instead of measuring from the center of an atom to the edge of the atom, we measure from the nucleus of one atom to the nucleus of another that's the same,
And cut it in half.
and cut it in half.
Yeah, that makes sense.
That because we can't see the edge of an atom.
Yeah.
Because of the electron cloud. So there's the picture of it. So
Yeah.
we take 2 atoms, we measure from nucleus to nucleus, and we divide by 2.
Right.
We call that the radius.
Like nucleuses, I might add. Don't forget this is a sample of the same stuff.
Right, it's sample A and sample A. Atom A and atom A.
All right, so atomic radius decreases from left of the periodic table to right, so decreases across the period.
And that doesn't make the sort of sense that I'd think it would.
No, because you're putting on more protons, more electrons. Oh, you're putting on more protons, more electrons. Larger positive, larger negative, tighter grip.
Okay.
Oh,
Right.
okay.
That nucleus is getting bigger, so it's able to hold on to those electrons a little bit tighter.
Yeah, and since protons, they're usually larger than electrons, right?
And then as we go from the top of a group to the bottom of a group, it's going to increase.
Which makes, that one makes really good sense.
Yeah, because you're adding more energy levels, more
Yeah,
orbitals, more
further away.
more electron clouds.
All right, so it's just the first one going across you might have to think about for a little while.
Start with lithium,
And then beryllium,
and then beryllium,
boron,
then boron,
carbon,
carbon,
nitrogen, oxygen, fluorine, and neon.
So neon's the smallest in that period.
Going across, yep.
So I know I'm in a new period because suddenly it gets larger.
Yeah.
Because we added another
Energy
level.
levels.
Okay.
Sodium,
So sodium has a 3rd energy level, and that's why it gets bigger.
yep. Magnesium, aluminum. I said that wrong. Aluminum,
All right.
silicon, phosphorus, sulfur, chlorine, and argon.
And after argon, I've gotten to the smallest in the group, so I know that I must be going to the 4th energy level
Yep,
with potassium.
yeah.
All right, we won't worry about doing any more of these. But I get the idea. The trend is to go down in each group. As you go down, as you go across the group, it gets smaller.
Yep.
I have such an affinity for this class.
Electron affinity, the
Uh.
energy change that occurs when an electron is acquired by a neutral atom. Okay, so a couple of things that hits my mind. Thing number one, this is kind of the opposite of ionization energy, correct? Ionization energy was the loss of, this is the gain of.
This is the gain of, yeah. So this is the almost the exact opposite.
Right, and this is a standalone atom, correct?
Standalone, it's all by itself, yeah.
So the affinity of a standalone atom to gain an electron.
Correct.
I would imagine the right-hand side of the periodic table has a larger electron affinity because they're supposed to gain electrons.
Right, they want to.
Yeah.
They tend to want to because they have lots more and they don't want to lose all of them. All right, so electron affinity, you're right, Mrs. G. If you look at the arrow in the picture here, electron affinity does increase as you go across.
Yep.
It's the amount of energy increases. Now the other thing, the other part of the trend is the up and down part of the trend. It turns out that it's easier for a atom at the top of the group to gain an electron.
Oh yeah, they're smaller and it gets in close and less
Exactly.
energy is released.
Exactly. So because of the positive nucleus, because of that nuclear charge, it's going to be able to suck in an electron a lot easier than
so it's
something down near the bottom.
Going to get nice and close, lots of energy released, very little energy retained. Okay, that makes sense.
Now, if you actually take time and you look at this table here and you analyze it, there are a lot of exceptions. Remember, guys, this is just trends. So as you go across, you get an increase. As you go up, you got an increase. Okay.
Wait, didn't we just do electron? Oh, this is electronegativity.
Yeah, electronegativity, a little bit different.
Okay.
And I think this might be the last one.
Ooh, cool.
All right. So electronegativity is the measure of the ability of an atom to attract electrons when in a compound. So
Okay.
that's how this is different from the last one. The last one was single
standalone
atoms.
atoms.
This is when you're in a compound.
All right.
Okay. The trend is you're going to increase as you go from left to right. So an atom's going to be able to attract electrons better, and that makes sense, right?
Yep.
And you're going to decrease from top to bottom. Or another way to say that is the same way as we said on the last slide. You're going to increase as you go from bottom to top. It's easier for smaller atoms to pull in electrons.
Well, electronegativity is completely different than electron affinity, but it has the same trend, doesn't it? Increases across, decreases down.
Mm-hmm.
Huh.
Yeah. And we can see here that as we go across,
Starting at lithium,
we got lithium,
beryllium,
beryllium,
boron,
boron,
carbon,
carbon,
nitrogen,
nitrogen,
oxygen,
oxygen,
fluorine.
fluorine.
And fluorine has no equal.
Fluorine is the largest electronegativity on this whole chart.
Yep.
Yeah.
Nobody beats fluorine out.
Nobody ever,
Ever.
anywhere on the periodic table?
Nowhere on the periodic table. Fluorine is it.
So it increases as you go right and up, and there's nothing really above fluorine.
Nope.
So yeah, because helium is
Noble gas.
it's not gonna attract electrons. Noble gas.
Back. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine.
Okay.
And they don't even bother putting the noble gases because
No,
noble
there's-
gases.
They don't really attract electrons. They don't tend to form compounds.
The neon argon, yeah.
It's way too hard to make them form compounds, so
Yeah.
we don't put them on here.
Okay.